what else? So that's the last day we'll have class, and then your final, let me just grab that real quick, just in case anyone doesn't remember when it is. So if you don't already know, 2 weeks next, oh my goodness, my words aren't working. There's the 2 days next week, Monday and Tuesday, and then Wednesday, Thursday, Friday are like all reading days, so y'all just get to like study your butt off. And then our final exam is Thursday, December 10th. So let me write that right here really quick. I'll erase it in a second, but Thursday, the 10th at 12:30. So it's going to be online because, of course, all of them have to be online this semester. So it'll be through Blackboard. What I'm planning on doing is I'm probably going to post like a dummy test, if you will. I'll probably just throw together a bunch of old quiz questions that are already up on Blackboard, just to give anybody who hasn't taken anything through Blackboard an idea of like the setup and what it's going to look like so that you're used to it. But otherwise, your exam will be going up Thursday the 10th at 12:30. You'll have a 2.5-hour period to do it because that's what the university gives you. I usually try to write, an hour 45-minute-ish exam. So I don't write a 2.5-hour exam by any means. But a little bit longer than just a little bit longer than a normal exam. You'll have the 2.5-hour time frame to take it, and yeah. So that's the thing. So that's all coming up. I'll talk about the final a little bit more next week, I think, because I haven't quite figured out exactly some of the specifics about how I plan to do it or the setup or anything like that. There will be a review packet thing, like there have been for the rest of the exams. I'll also create one for the final. Also, before I forget, there is the final homework assignment. So there's one last homework assignment. It got put up on WebAssign a little while ago. And because I don't want to make you think that I'm trying to make you do homework over Thanksgiving, instead of having it due on Tuesday, I pushed it to Thursday of next week, next Thursday. After today, you'll have everything you need to do it because we're not doing content next week. So you can do it this weekend if you want to and pretend it's due on Tuesday, but it's due next Thursday instead. That's the last one. All right, anyway, I think that's all the hoopla I wanted to talk about. So let's get into these notes. Discrete probability. So probability tells us how likely something is to happen. I need to make this smaller. So the probability of an event occurring is some number between 0 and 1. So it's going to be that's less than 1, where 0 means that it's impossible, it's 0% likely, and 1 meaning that it's certainly going to happen, so 100%. We're usually also going to express these numbers as percentages, so we'll usually find the decimal and then, well, the percent usually ends up being a decimal too, but we find the decimal representation and then also write it as a decimal. So say we have 28 people in a class, 16 are girls and 12 are boys, and if a name is randomly selected from the class roll, how likely is it that the name belongs to a girl? Well, since there's 16 girls, so essentially there would be a 16 out of 28 students that are girls. So we essentially have a 16 out of 28 chance. So if we calculate what 16 over 28 is, 16 out of 28, if you will, we get 0.5714. And I mean, it continues, but which we would then rewrite. So reminder for writing things, it's percentages. If you've forgotten, you take the decimal and you move it 2 points to the right, and then you just put the decimal in its new spot, and voila, it's a percent. So this would be 57.143%. So essentially, if you just picked a random name, there's approximately a 57% chance that it would be a girl's name instead of a boy's name. So in this one that we just looked at, one moment, please. Sorry about that. So in that one that we just looked at, we were essentially asking how many students are girls. So it kind of fits a format of saying blanks have a certain property. So if we actually translate that into set theory, so stuff we looked back at chapter 2, we could essentially ask how many elements of a set are in the subset of students that are girls. So essentially you have this big set of students and you have a subset of girls, and you want to know how many students are in the subset. Or you could also think of it as how many elements of the set U, the bigger set, are in some subset A. So you have some big set, how many of them actually end up in this subset? Or what percentage of elements in U are in a subset A? So if we think about it in terms of a percentage, well, that sounds a little bit more like probability. So that's how we're going to really phrase them, but we are going to kind of think about some of these as thinking about having a larger kind of all-encompassing set and then only trying to figure out the pieces of a smaller set. So if we want to know the percentage of elements of a bigger set U that are in a subset, we just need to set up the ratio like we just did. We had 16 girls out of 28 students, so we just did 16 over 28. So, definition. Suppose A is a subset of a non-empty finite set U. The probability that a randomly chosen element of U lies in A is the ratio. So we're going to say P of A for the probability of A. It's going to be the cardinality of A divided by the cardinality of U. Essentially, how many elements are in the subset that you're looking at divided by how many elements are in the larger set. So the set U is going to be called the sample space. Sample space. And the set A, the thing that we actually kind of care about, is going to be called the event. So we want to look at the probability of an event happening. So hold on a couple seconds in case people are writing that down before moving on. But that's essentially the big chunk of what we're going to talk about first. Is we're just going to find out a bunch of probabilities of some events. All right. Scrolling. So say we want to roll 2 6-sided dice and we want to know the probability that we roll a 7. Now, I should clarify, this is like you roll one die and then you roll the other one. So we're not going to consider them to be rolled at the same time. So something like a 1 and a 6 is going to be counted different as a 6 and a 1. So it's like we're going to roll them separately. So let's think about this in terms of kind of the set language that we set this definition up with. So if we look at our set U, our kind of all-encompassing set, that would be the set of all possible combinations. All possible combinations. I'm not going to actually write out that set because it would take a while. You know, we'd have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. You know, it'd be a very long list. So let's not list all of that set. But then if we think about the set that we actually care about, that would be the set of combinations that give us 7. So the set combinations that give us 7. Or you could say like that sum to 7 or something like that. So let's go ahead and write out that set. And let's write it as like coordinate pairs in a way. So like the coordinate pair, the first number is the roll of the first die and the other one's the roll of the second die. So if we rolled a 1 on the first die and a 6 on the second, that would give us 7. If we rolled a 2 and a 5, a 3 and a 4, a 4 and a 3, because again, we're kind of counting this, we're not throwing the dice at the same time. So we're considering, you know, a 1 and a 6 different than 6 and a 1. Or maybe they're different color dice and you can throw them at the same time, but then if a red dice gives you 1 and the blue dice gives you 6, it's different than vice versa. So we know that the cardinality of A, well, we can just count up those elements because it was easy enough to list out. There are 6 elements in that set. And then we would need to know the cardinality of U, how many possible combinations are there? Well, instead of writing it all out, let's just think about it kind of in terms of kind of the chapter 4 material we've already talked about. So we kind of have 6 choices for the first die, and then we have 6 choices for the second die. So since they're, disjoint and they're affecting each other in a way, like it's not like the 2 separate roles. I don't know how I want to phrase it. It's not like that one where we had like, you have 6 salads and 7 burritos. How many choices do you have? So it's not the addition principle here, because essentially these are being grouped together in one combination. But anyway, so there's 6 choices for the first, 6 choices for the second. So there's 36 total combinations. So what is the probability that we'll get a sum of 7? Well, we'll take our cardinality of A divided by our cardinality of U. So 6 divided by 36 is 1/6, which is 0.16 repeating. So if I wanted to change that to a percent, it would be 16. And let's go ahead and just take like 667. So I know it's 6 repeating, but let's cut it off eventually. So there's about a little under a 17% chance of getting a combination that gives you a 7. That makes sense? Questions, concerns about that? Okay. So let's do another one. So recall from example 7 and 4.1, or just read it because I kind of tell you what it was back down here. So it says Illinois license plates were used to, sorry, I can't read. Illinois plates used to consist of either 3 letters followed by 3 digits or 2 letters followed by 4 digits. We determined that there were 24,336,000 possible Illinois license plates. Now suppose you get a random Illinois license plate. What is the probability that your plate contains the word cub or socks? So first of all, we have to recognize that since we have 3 letters, we have to be in the 3 letters, 3 digit situation. So all of the 2 letter 4 digits are just like, too bad, so sad. We're still going to take into consideration the fact that there are the 24,336,000 plates, because we do have to consider those plates. But in terms of the ones that would give us a plate that contains cub or socks, it would have 3 digits, 3 letters combination. So let's think about this in terms of our sets again. So our entire, kind of universal set, if you will, since we call it universal set. So kind of the universal set here would be the set of all license plates. Set of all license plates. Maybe I should say Illinois license plates, but who cares? And the cardinality of this set, we know because we found it in a different section, was that 24,336,000. So now if we consider the set that we actually care about, this would be the license plates containing either the word cub or socks. So again, we're essentially in the 3 letters, 3 digit situation, because there's no way to get cub with just 2 letters. So we kind of have 2 different options. It could either be cub and then 3 digits, or it could be socks and then 3 digits. Now there's 10 digits, so there's essentially 10 cubed ways to fill in those digits. To fill the digits. Same way for the second one, there's 10 cubed ways to fill the digits. So these 2 situations are completely disjoint. They don't affect each other in any way. So we'd be using the addition principle to figure out how many there are. There's no way that these two types of situations intersect in any way or affect each other. So essentially the cardinality of A, this set that we actually care about, would be whatever 10 cubed plus 10 cubed is. Well, it's 2,000. So there's essentially 2,000 license plates that would either have the word cub or socks in them. So if we want to know the probability that that happened, so the probability, of this situation happening would be the cardinality of A divided by the cardinality of U. So 2,000 divided by our 24,336,000. So a very small number. So whenever you're writing these, I would suggest taking a decent amount of decimal places, especially since you change it over to a decimal usually after the fact. And especially in this case, since there's so many zeros in the beginning, take all of the zeros and then, take at least 2 or 3, more like 3 or 4 probably is better. 3 or 4 actual numbers that aren't 0. So here I'd say 0, 0, 0, 0, 8, 2, 1, 8. Which if we change over to a percent, we move the decimal place 2 spaces over to the right, we get 0.008218%. So not very likely. So if you're ever in Illinois or see an Illinois license plate and it actually has the word cub or socks on it, actually I don't know if this is still how they do their license plates. Never mind. Don't mind me. If you see one, even if it's not how they do their license plates anymore, it's probably a small probability that it happened. Anyway, questions, concerns on that one? All right, I'll wait a couple seconds in case people are still writing something down. Sorry, I got distracted. All right, next one. An urn contains 7 red balls, 7 white balls, and 7 blue balls. A sample of 5 balls is drawn at random without replacement. And let's just go ahead and assume that we're going to draw them all at the same time, so order's not going to matter here. What is the probability that the sample that we pick, so the 5 balls that we pick out, contains 4 balls of one color and 1 ball of another color? So the sample space, essentially our universal set, if you will, is going to be the set of all possible 5-ball selections. Now, since order doesn't matter here, this is essentially going to be a selection, which is related to our combinations. So we can say that the cardinality of this sample space is going to be 1, choose 5. So there are 21 balls in total, 7 plus 7 plus 7, and we're choosing 5 of them. So 21 choose 5 would be 20,349. Let me just write the factorial notation in case anyone likes the factorial notation, but there we go. Now, essentially, the way we can think about doing this event that we want to happen, this choosing the stuff that we choose having 4 balls of one color and 1 ball of another color, we can kind of think about it in kind of like a sequence where the first thing we need to choose is to choose the color of the 4 balls. So the balls that should have the same color. So we can think about it as saying, okay, well, we're going to choose the color of that ball first. Those balls, I should say. And there are essentially 3 choices for that. There's 3 colors, so we can pick one of them. And then we would have to go about actually choosing the 4 balls of that color. Now, I should clarify, this isn't like something where you're standing in front of the urn and you're going, I'm going to pick out 4 white balls, and then you sit there and actually pick out 4 white balls. We're just trying to consider how many ways there are to do this and breaking it down in this way of, well, you have a choice of color, and then you have to figure out how many ways there are to choose 4 balls of that color, that type of thing. So it's kind of like just helping us figure out how many choices, how many ways we have to actually do this. So we need to figure out how many ways there are to choose those 4 balls of that color. Well, there are 7 balls of each color, so we would have 7 choose 4 for that situation. If we have 7 white balls and we must have chose 4 of them, there are 7 choose 4 ways to do that. So there are 35 ways to do that. And then you can think about it as that we have to choose the color of essentially that remaining ball that we're going to need to pick. So the remaining ball. Well, we've already chosen one color, the color of the one that was supposed to be for the 4 balls, so there's only 2 choices left. And then we have to figure out how many ways there are to choose the ball of that color. So essentially you choose your last color, and then you have to figure out how many ways there are to choose one ball of that color. There are 7 balls of each color, so 7 choose 1 is 7. So essentially now we've broken down kind of this event into stages, if you will, to help us figure out how many ways there are to do this. So essentially that's going to help us find that the cardinality of this event set, if you will. So we essentially have 3 choices for the colors of the first 4 balls, times 35 ways to actually choose those 4 balls, times 2 choices for the remaining color, times 7 ways to choose a ball of that color. So there's essentially going to be 1,470 ways to make those choices. So there are going to be 1,470 possible combinations that will give us 4 balls of one color, 1 ball of the other color. So if we want to know the probability of that happening, because remember, we don't care about how many there are, the thing we actually care about here is the probability that it happened. So the probability of that happening would be the cardinality of A divided by the cardinality of our U. So 1470 divided by 20,349 gives us 0.07224. And converting that over to a decimal, move that over 2 spaces to the right, we have 7.224% chance that just picking 5 balls randomly will give you 4 balls of one color and 1 ball of the other color, of another color, I should say. Questions, concerns about that one? That one was a bit more in depth. Okay. I'll wait a couple seconds as usual. We're checking through this pretty quickly, so this isn't probably going to take all class. But all right. Okay. Please don't hesitate to stop me if you have questions. Even if it's asking me to go back to something I already went past. So we have a multiple choice test consists of 8 questions, each of which has 4 choices. Each question has a correct answer. William guesses randomly at each answer. What is the probability that he gets at least 7 questions correct? So let's figure out our 2 sets first. So kind of our sample space is the amount of ways you have to fill out the test. So ways to fill out the test. So the cardinality of this sample space, well, there are 4 choices for 8 questions. So you essentially have 4 times 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 4, otherwise known as 4 to the 8th. So we have 4 to the 8th, or 65,536 different ways we could fill out this test randomly. But the space we actually care about are the ways to get 7 or 8 right. Because there are 8 questions total, and we were asked the probability that he gets at least 7 correct. So we need to essentially count up the ways to get 7 correct or 8 correct. So we kind of have two things we need to consider: getting 8 right and getting 7 right. So essentially, to get 8 right, you essentially have to choose the correct answer for every single question. Well, since there's only one correct answer, let me write this. Chooses correctly 8 times. So you have one correct answer for 8 questions. There's only one way to do that. So there's only one way out of 65,000 ways to get it completely right. Now, if you're only going to get 7 right, you essentially have to miss one of them. Now, we also have to think about it not only as you miss one of them, but you also kind of have to choose which one you miss. Like, do you miss the first one, or do you miss the 7th one? Do you miss the 6th one? Do you miss the 3rd one? It's all going to give you a different combination depending on which one you get wrong. So we have to choose one to miss, one to get wrong. And so there are 8 questions, and we're going to choose one way, choose one of them to miss. So there's 8 ways that we can choose, 8 questions we can essentially choose to miss. There are 3 ways. I'm going to stop using miss, and I'm going to say 3 ways to get it incorrect. I feel like miss is probably a little too wishy-washy of a statement. So then there are 3 ways to get it incorrect, because there's 4 options for that question. Only one of them is right, so there are 3 of them that are wrong. So even for each question that you could possibly get wrong, there are 3 ways you could get it wrong. And then you have to be correct 7 times. Now, if you're correct 7 times, that means you chose the correct one choice for 7 times. There's only one way to do that. Okay. So essentially, the amount of ways to get 7 right is to consider that there's 8 choose one ways to pick a question to get wrong. There are 3 ways to get that question wrong, and then there's just one way to get the rest of the 7 correct. 8 choose 1 is 8, so we essentially just have this as 8 times 3, so 24. So there are 24 ways that you could get 7 right. 8 ways to pick which one you're going to get wrong, 3 ways to get it wrong, only one way to get the rest of the 7 of them correct. So if we want to figure out now the actual probability of what we actually cared about, so we care about the probability of getting either 7 or 8 correct. Getting 7 correct and getting 8 correct are completely separate, completely disjoint situations. They don't affect each other in any way. So we're going to add those 2 amount of choices together. So we're going to have 24 plus 1 divided by the total amount of ways, which was the 65,536. So essentially 25 divided by that 65,500. This will give us 0.0038. Move the decimal 2 spots to the right. 0.038%. So not a very good outlook there for just random guessing. But anyway. Questions, concerns on that one? Okay, I'll wait a couple more seconds as usual. All right. So shifting ever so slightly, but not really. if this will allow me to scroll. There we go. So in example 1, we looked at the likelihood of drawing a girl's name, which was 16 out of the 28, which was approximately, let's just say 57% for our sanity. So what would be the likelihood of not drawing a girl's name? Well, in that case, it would be easy enough to just take the amount of boys divided by 28. But there's another way you could think about it. So we would have to, in this case, we would have to draw a boy's name, of course, which essentially has a 12 divided by 28. And let's just round that to 43% for our sanity. Now, the probability that event will happen and the probability that the event will not happen has to add up to 100%. So essentially, another way you could think about this is that if you wanted to know the probability of choosing a boy's name and you already knew the probability of choosing a girl's name, you could essentially take 100 minus the probability of choosing a girl's name. Because if those are the only two choices for that scenario, then the probability of choosing either one or the other had to add up to 100. So if there's a 57% chance of choosing a girl's name, then there has to be 43% chance of choosing a boy's name. And sometimes in this situation, it's barely helpful because it's easy enough to just find the actual probability by doing the 12 divided by 28. But in some situations, it's harder to find a probability that something will happen than it is to find the probability that it won't happen. So sometimes it's easier to find the probability that it won't happen and then essentially subtract that out of 100%. Which is essentially what this theorem is trying to get at. It says if A is a subset of a non-empty finite set U, let A prime be the complement of A. So remember, the complement is essentially everything in that universal set that's not in A. So like the complement of the set of girls in the first example would be the set of boys. So if we want the probability, if the probability of A happening is P, then the probability of A complement is going to be 1 minus P. Because since the p-value would be a decimal less than 1, we're not working with the percents, so we're not doing 100% minus p. If you changed that p over to a percent, then you would subtract it out of 100. But if you're working with the decimal representation, then you would just subtract it from 1. So, say multiple choice test consists of 8 questions, essentially the same question we just looked at. So 8 questions, each of which has 4 choices. Only one answer is correct. William guesses randomly. What is the probability that he gets fewer than 7 questions correct? So in this case, if we were doing this kind of forward, if you will, we would have to figure out the probability of getting 0 right, of getting 1 right, 2 right, 3 right, 4 right, 5 right, or 6 right. So we would have to find all of those probabilities and add them up. So in this case, even if we hadn't done it already, it would probably be easier to just find the probability of getting 7 or 8 correct and then doing this kind of backwards technique, if you will. But since we already have that, that makes it even easier. So essentially we know the probability. Can I spell probability? There we go. So we know the probability that he gets at least 7 correct is 0.00038, or it was that 0.038%. So since we already know that, then we can pretty easily find the probability that he gets less than 7 correct fewer than, let's call this our event A now. So the probability of getting fewer than 7 questions correct is essentially going to be 1 minus this 0.00038. 1 minus the probability that he gets at least 7 correct. I trust and believe we could type that into a calculator. We get 0.99962. So a 99.962% chance that he gets fewer than 7 questions correct. And again, just to stress, I know technically we already solved pretty much the other half of this question already. But even if this was just a question given to you right off the bat, if you view it as either a choice of finding 0, 1, 2, 3, 4, 5, 6, that's technically 7 probabilities and adding them together, or just finding the probabilities for 2 things and adding them together and doing a little subtraction, the second one sounds a little faster. So you sometimes can think about it in 2 different ways. If it's easier to find the probability that it's not going to happen and then subtract that from 1, that sometimes can help. All right. Questions, concerns? Maybe I lied. Maybe this will take all class. Anyway. Okay. Suppose there are 10 defective machines in a group of 200. A quality control inspector selects a sample of 3 machines to test. How likely is it that the inspector discovers a defective machine? So the way we're going to look at well, let me set up a couple things first. Let me do a couple things first. Let's look at our sample set. So our sample set, the kind of universal set, if you will, would be essentially all possible selections of 3 machines. How many actual ways could he just pick 3 machines out of these 200? So all possible I can't spell today. Selections of 3 machines. So there's 200 machines and you're choosing 3 of them. It doesn't matter the order, so it is a choose, not a permutation, not an arrangement. So we're choosing 3 of them. This would result in 1,313,400 ways of choosing 3 machines. Now, instead of trying to figure out whether or not he's going to get a defective one, why don't we look at how many ways there are to get, no defective one, to get, all of the machines that you pick are fine. So as 10 are defective, that means there's 190 of them that are not. So how many ways are there to choose a set of, perfectly fine machines, working machines? So if there are 190 machines that don't have a defect, and I want to choose 3 of them, how many ways are there to choose just a set of purely working machines? There would be 1,125,180 ways. So this is essentially ways to choose a sample with no defects. Because again, there were 190 of them that didn't have defects. So if we just choose 3 out of that 190, we'd be good to go. That one in the middle looks a little silly. There we go. So essentially, if we find the probability of doing this, then we can do our subtracting way to figure out the probability of actually getting a defective machine in that set of 3. So the probability of no defects, probability of no defects, would be this 1,125,180 divided by 1,313,400. Trust and believe we could type that into a calculator. 0.85669. I'm not going to bother with changing that over to a percent because it's not the thing I actually care about. And when you do the little subtraction technique, you don't necessarily use the percent. So then if we want the probability of finding a defect, or the fact that one of the 3 that you chose actually has a defect in it, would be 1 minus this 0.85669. That will give us 0.14331. So since this is the answer that I actually care about, I'll actually switch this back over to a percent. So this will switch over. We didn't anyway. So about a 14.331% chance that the selection of 3 machines will have one of them, at least, having a defect in it. So instead of trying to count all the ways to find the probability of actually finding a defect, we instead said, well, maybe it's probably easier to find the amount of ways to not get a defect, and then just do this subtraction technique. Questions, concerns on that? That's the last example for the one like that. So if you have questions about that idea, also let me know. We're going to move on to a slightly different idea. So I'll wait like a couple seconds in case people are still writing that down. All right. So last thing we have to talk about is something called expected value. So a random variable is a numerical result of a random experiment, like rolling a die or flipping a coin. So the notation P of x equals x is gonna, so note that the one's a capital X, the other one's a lowercase x, is gonna denote the probability that a random variable x takes on the value x. So capital X is usually what's used to denote a random variable. And then the little x is denoting the value you want to look at. So in example 2, the one where we were looking at the probability that the sum of a two dice roll would be 7, it would be the probability of x equals 7, the probability of that random variable, those dice rolls, equaling 7. So if we repeated a random experiment several times, say you flip a coin 50 times, 100 times, whatever. So you're doing a random event a bunch of times and you're going to record the value of each random variable each time. So say you're flipping a coin, you're going heads, tails, heads, heads, tails, heads, tails, tails, heads, tails, whatever. If you record all those results and then you average those results. So in terms of like the head and tails situation, you would kind of think about it as giving them both a number, say heads is 1, tails is 0. So you would kind of average those results. And we would get an estimate of the probabilistic average. Now it's a little bit weird to think about because in something like a dice roll, I don't know what the actual probabilistic average of a dice roll is, but say you did an event with rolling a die and you found the probabilistic average to be like 3.5. You can't actually get a 3.5 on a die, but that's essentially what it's telling you is over that kind of, over those, all of those experiments that you did, on average, you got around a 3.5, which probably means on average you got maybe between a 3 or a 4. So I'm not saying that it doesn't make sense, but I'm also saying that there's a little bit of a weird context to these sometimes. So anyway, the probabilistic average of a random variable is going to be called the expected value. Expected value. So say we have some x sub 1 through x sub n being all the possible values of a random variable. So like for a die, it would be 1 through 6. Then the expected value of a random variable x, which is also going to be denoted as e of x. And this is going to be defined to be the expected value is going to be the sum from I equals 1 to n of x sub I. So this has scary sigma notation, but when we do our first example, it'll probably make a bit more sense of what this is, what I mean by this notation. To say a little bit about it though, this x sub I, that's going to be essentially the value that the thing is going to take on. So say we were doing this for a die, so our values were 1 through 6. We would have the value in the first term being 1, the second term being 2, the second term being 3, all the way up to 6. And this is the probability of getting that value. So again, if we were talking about a die roll, we would find the probability of rolling a 1, and so we would do 1 times the probability of getting a 1 plus 2 times the probability of getting a 2, and so on and so forth. And all of this together essentially gives us a weighted average in a way. That's going to tell us this probabilistic average. So that's what's happening here. So let's do, we're going to do 2 examples of that. And then we're done. So wait a couple seconds in case people are still writing that definition down. Okay, let me try to leave it in a little bit. There we go. And I'll scroll down a little bit more in a second. So a lottery pick 3 allows you to pick any 3-digit number between 000 and 999. A randomly chosen 3-digit number is announced as the winner. If your number, excuse me, if your number matches the winner exactly, you win $580. If you have the same digits as the winning number but in the wrong order, you win $80. What is the expected value of your winnings, assuming you choose a number with 3 distinct digits? Okay, so essentially the random variable we're looking at is going to be the amount of money you win. So essentially those are like your choices. So we're going to have the first option is 0. You just don't win anything. Wait, sorry. Yeah, there's lots of X's floating around. So the one choice is that you win nothing. The second choice is that you win $80 if you match the digits, but just in the wrong order. And then the third option is that you win the $580 if you actually got the right number. Sorry, I'm just thinking about something really quick. I don't know why they specify that. One moment while my brain explodes. Boop ba doo ba doo. Wait a minute. What? Okay. Magic. So as I think I've mentioned before, I steal these notes from somebody else. And so I stole them. And now suddenly it doesn't include this last, nope. Doesn't include this last little bit, which I was very confused about because I was like, I solved this as if we weren't assuming that. So let's not assume that they're distinct digits. Let's just assume that you choose a 3-digit number because that's what the thing is actually asking you to do is choose a 3-digit number. Sorry about that. So just the expected number, no hold barred on the number you can pick. You can pick any 3-digit number that you want. Oh, I was still writing in purple. Whoops. Anyway, sorry. So the random variable is still, again, the amount of money you win when you either win $0, $80, or $580. So essentially what we want, so let me write the, scary sum notation here, is we will want the sum from 1 to 3 of essentially these random variables, these choices that we have for the amount of money that we're going to win, and then the probability that we actually get that much money. So if I write this out a bit more fully, we're going to take essentially 0 times the probability that the value we get is 0, plus 80 times the probability that we actually win $80, plus 580 times the probability that we actually win $580. So that's what that big scary sum is trying to say. We take the actual value, the possible value, times the probability of getting that value. Now, if we think about the amount of ways we can choose a 3-digit number, which again is why I decided to erase that part about distinct digits, there's 10 cubed ways of choosing a 3-digit number. Ways to choose a 3 That doesn't look like an A. Digit number. So essentially that's going to be, this is essentially going to be our U, kind of universal set, if you will, to be able to find our probabilities. So if we think about the probability for all of these, so let's start with the $580. So to win the $580, you have to match the number exactly. So there's only one way to match exactly. Oh, also, if you printed these notes out before a couple hours ago, you'll run out of space. So I added a more spaced out version. So I'm sorry if you have the less spaced version, you might want to grab an extra sheet of paper. Anyway, so there's one way to match exactly. So the probability of doing that would be 1 over 10 cubed, essentially the number of ways to choose a 3-digit number. So 1 over, yeah, right? Why is my brain not working? Yeah, 1 over 1,000. So 0.001. We'll leave it as a decimal for now. Well, actually, because we kind of need to, because the probabilities that we put in here, we want to leave as a decimal. One second. Sorry about that. Okay, so what am I saying? We want to leave it as a decimal. So there's one way to match exactly. So if we think about the way to essentially match the correct digits, but in the wrong order. So essentially to choose a 3-digit number, now this is doing, okay, whatever. I'm going to forget my notes and just keep doing it that way. So essentially to choose any 3-digit number, you have 3 choices for the first number, 3 choices for the other number, and 3 choices for the third number, right? So 3 cubed ways to choose a 3-digit number. Now, if you think about it, if you have to match the digits, why is my brain breaking? I'm really sorry. My brain's exploding. Right. Sorry. There's 3 digits you'd have to choose from. You know, if the winning number is 231, you must have used those 3 numbers in some order. So there's 3 choices for the first, 2 choices for the second, and only 1 choice for the third, because you have to use those 3 numbers. Even if it was, you know, 4, 4, 4, think about it as 3 choices for one of the 4s, 2 choices for one of the other 4s, and 1 choice for the last 4, if that makes any sense. So there's essentially 6 ways that you could rearrange those 3 numbers, right? So there's essentially 6 ways that you could rearrange a 3-digit number. So if you think about matching the digits, so there's 6 ways to write a 3-digit number, but that would mean that there's 6 minus 1 ways to match the digits, but not win, right? Sorry, I butchered that a whole lot. I'm so sorry. So essentially, if there are the 3 numbers that you need to have chosen, you have essentially 3 choices for the first blank, 2 choices for the second, 1 choice for the third. But then we have to essentially take away that one way that would actually match exactly. Let me know if you have questions about that. Again, I know I kind of butchered that a little bit at first. I'm really sorry. So essentially the probability of that happening would be 5 divided by 10 cubed. So 5 over 1,000. So 0.005. So that's the probability that you would pick the same 3 digits, but just in a different order. And then we need to consider the probability of losing. Now, to consider the probability of losing, let's just consider essentially 1 minus the probability that you actually won something. So the probability to lose, which would be the probability that our value is 0, would be essentially 1 minus this 0.001 minus the 0.005, which gives us 0.994. Because if you don't get $580 and you don't get $80, then you must have lost. So instead of just trying to find the actual probability of losing, let's just take 1 minus the probability that you won. And there were 2 choices for winning. Does that make any sense? Any questions about any of those 3 probabilities before I finish the question? Because we're not technically fully done yet. Any questions on how I found any of those? Okay. So then the actual expected probability, ooh, I'm almost running out of space. So let me rewrite this again, because I've kind of scrolled past it at this point now. 80 times the probability that we get $80 plus 580 times the probability that we get $580. So the probability, sorry, you're lost in this. Is there a certain part that I lost you at, or just kind of everywhere? Is the sauce overwhelming and consuming your brain? You don't know it? Okay, let me try to start this one over a little bit. Okay. Can I just explode this? Can I? Maybe I can't. I want to explode this. Whoa, that's not what I wanted to do. That's more exploding than I was hoping to do. Whoosh, whoosh, whoosh. Can I just make all that go away? Woohoo! I did it. Okay, let's just start over. Now that my brain won't explode when I do it because I've already done it. Here we go. So again, we're not assuming that we're choosing 3 distinct digits. That is getting out of here. Okay. Random variable is just a name to denote what your choices are. Like, what are the possible things that could happen? So essentially, what are the things that could happen? You could lose, which essentially means that you win $0. That's a weird way to phrase it, but technically that's what it would mean to lose, is you would win $0. You can essentially match the digits, which would win you $80, or you can match completely, which would win you $580. So essentially, when I say random variable, all that's meant by random variable is what are the options for the thing you're looking at. Are you looking at a coin? Then your options are then your random variables are head or tails. Are you rolling a die? Then your random variables are 1, 2, 3, 4, 5, and 6. Well, if it's a D6. If it was a D4, then your choices would be 1, 2, 3, 4. If it's a D20, you know what I mean. So essentially, when I say random variable here, I just say, what are our choices that we're looking at? What are the things that could happen? I could lose, I could match the digits, but not in the right order, or I could match completely. So those are my 3 random variables. Those are my 3 choices. So what I'm asked to find is I'm asked to find the expected value, which is essentially a sum of kind of the choice, the option, in this case, the amount of money I can win, times the probability of that actually happening. So essentially we need to take, well, we could win $0 and I need to find the probability that that would happen. So I need to find the probability of losing. And then I'm going to add that to $80, which is the amount of money that I could win. I could write them in different colors, maybe. I'm trying to make one like very straight lines and the other one's kind of curvy, but I can write that one as a big old red X if you want. But I am trying to, the difference between X and X is what I'm trying to do. But I'll just do a big scary red X. And then your third option is winning $580, and then we have to find the probability of that actually happening. So essentially you have the values that you could be, and you have to find the probability of being any one of those values. So again, if we were looking at a die, 1 through 6, we would then have to find the probability of rolling a 1, probability of rolling a 2, probability of rolling a 3, and so on. So here we have 3 options: win $0, win $80, win $580, and now we have to find the probability of each case. So if I then forget about that for a second, this is my goal, this is what I want, but I need to find these things first, these probabilities. So let's start with the probability of our random variable being 580, which means that we win the $580. Well, wait, I need to do one tiny thing before I consider that. We need to know how many ways there are to choose a number. So essentially, what is the kind of universal set, if you will? Okay. The universal set is the set of all 3-digit numbers. So how many ways are there to do that? You have 10 choices for the first digit, 10 choices for the second digit, 10 choices for the third digit, so 10 cubed, so 1,000 ways to choose a 3-digit number. So the probability of winning $580, well, what had to happen to win the $580? This meant that we had to match the 3-digit completely. Now there's only one way to do that. Like there's a set 3-digit number, that's the answer. There's only one answer. There's 1,000 things to choose from. So the probability of choosing the correct 3-digit number is 1 out of 1,000, which is 0.001. So that is going to give us the probability that we win $580. So we're going to need that. And then we need to consider the probability of only winning those $80. And this is the one where my brain exploded, so let me try to do this a bit better this time around. So we essentially have to match the digits in the wrong order. So if you think about this one, there's 3 digits and you just have them in the wrong order. And if you think about the amount of ways that you can rearrange 3 digits, so you essentially have 3 digits, you want to put them in an order. To arrange 3 digits, so number of ways to arrange 3 digits is 3 times 2 times 1. You have 3 choices for the first digit, 2 choices for the second digit, 1 choice for the third digit. So essentially, I give you 3 digits. I say rearrange 7, 2, and 5. And so essentially, out of 7, 2, and 5, you can choose, there's 3 options for the first, then 2 for the second, then 1 for the first. So there's essentially 6 ways you can rearrange any 3 digits. Now, out of those 6, one of them was actually the winning arrangement. One of them would have actually been the arrangement that won. So we don't want to count that in this one because that was already counted in the probability of getting $580. So the probability of winning only $80 would be 6 minus 1 over 1,000. Because now there's 6 ways to rearrange 3 digits, but one of them's actually the winning one, so we want to take that away. Gives us 0.005. Is that any better so far? Maybe. And then we need the probability that, oh man, ran out of space. The probability that the value we win is 0. So essentially the we want to lose. That was supposed to be an S. Lose. Now, instead of trying to like directly find like from the ground up the probability of losing, since we already know the probability of winning something, we can essentially take 1 minus the probability that we're winning. So we can take 1 minus the probability of winning the $580 minus the probability of winning just the $80, which gives us 0.994. Now I'm still not done the question yet, but does that make sense on how I found all of those 3 probabilities? Okay. Hooray. I think part of it was seriously my brain exploded, and I get super flustered when my brain explodes and I feel real bad. Oh, don't do that. I need you to get smaller so I can shrink you. Ho ho. Okay. All right. So then to finish the question, what we essentially want to do is we want to come back up here and we want to actually calculate this expected value. Now that we have those 3 probabilities, we can plug them in and solve this expected value. So the expected value is going to be 0 times the probability of losing, which was our 0.994, plus 80 times the probability that we only win $80, which was 0.005, plus 580 times the probability of winning $580, which was 0.001. Plug that sucker into your calculator, you'll get 98 cents. Now again, this is where I kind of was saying, while they have a meaning, it almost doesn't make sense because this is saying on average you'll win 98 cents and 98 cents is not an option to win. But it's essentially like if you play a crap ton of times, the expected value that you would make is only 98 cents. So essentially your expected to win an average of only 98 cents. That's assuming you play a lot. Because I know if you only play once or twice or even just 3 times, you'll probably just lose every single time. But so essentially with expected value, you take, so your random variables are just the outcomes that you can have. So in this case, our possible outcomes was $0, $80, or $580. So you take those possible values and you multiply them by the probability of that happening. And then you essentially add up all of those pieces. And that gives you the expected value. Now, obviously, we have 5 minutes. I don't think that's enough time to do this last one. So what do I want to do about it? Since your class is a longer time, I think I'll talk about this one next time before we get into the review. So we'll do this one really quick. We jump into a review. I'll post the completed notes for it if anyone wants to look at it beforehand, but I'll talk about it real quick at the start of next class. And then again, I'll try to have a review put together for you guys. Otherwise, bring questions. If we don't get to the actual thing that I create, that's perfectly fine. So whatever floats your boat. But again, you do have one final homework assignment. It's on 4.3 and 4.4. So that's a thing. At this point, I'm going to stop rambling though. If you have questions, feel free to stick around. Otherwise, we're going to be done for today. And I hope you all have a safe and happy Thanksgiving. And I'll see you next week on Tuesday.